Welcome to this special edition of The Second Opinion. My name is Dr. Patrick Soon-Shiong, and I'm chairman of Los Angeles Times, as well as CEO of networks and biotech companies. Today is a very concerning day as we hit the highest rate of infections the country has seen. And I feel it's really important for us to bring with me today a specialist, Dr. Adam Brufsky, who is a specialist in cancer at the University of Pittsburgh, but has devoted his attention during this COVID time to this virus. He can speak to us and our readers to give us some insights into how to deal with this pandemic, and is there hope on the horizon? Where are we with the vaccine? But before I start, I have to make sure there's full disclosure that I run a company called ImmunityBio and networks. And networks is involved in this deep research, not only in cancer, but in COVID. And recently we just received FDA approval for our first clinical trial as a COVID vaccine. And I'd like to welcome Dr. Adam Brufsky, and who's going to give us his thoughts on how we need to deal with this. So welcome, Adam, and let's begin.
Thank you very much. Thanks for having me, Pat. Thank you very much.
So let's look at this resurgence, and if I could look at this today, and if you look at this map, it's really one of the darkest hours as we go through this cases on the rise of 75% in the United States. And how do we deal with this? How do we deal with this resurgence? If I may have the next slide, please. And I think the hope on the horizon are these vaccines in phase 3 trials in the United States. So I will try and with Dr. Brufsky go through how these vaccines work, what are these vaccines, how do you as a consumer identify which is best for you, should you trust these vaccines, which is in my mind, we should really put assurance in your mind that these vaccines are being developed with the greatest science. So Dr. Brufsky, maybe if you just want to comment on these vaccines that are in clinical trials, AstraZeneca's, Johnson & Johnson, Novavax, Moderna, and Pfizer, which I'm sure to the lay audience would say, we don't really understand the difference between these vaccines.
Yeah. Well, as I think you'll go through, I think you have some slides there in a few minutes. You're going to go through these. You know, the idea behind a vaccine obviously is to mimic an infection, right? Is to kind of without you having the infection. So, you know, what you do is you're trying to induce an immune response. You're trying to induce your own body to develop an immune response, what we call a memory immune response to whatever you inject, that when you eventually get exposed to real virus or a live virus, you're able to clear it faster, almost to boost your own immune system. That's the whole idea behind vaccines. And you know, this is nothing new. The first vaccine really came out in 1797. Edward Jenner actually used an activated kind of cowpox, really a cowpox vaccine, which was related to smallpox. And you vaccinated people with cowpox and realized that they would not get smallpox. And so in the intervening 23 years, we really have gotten very sophisticated, especially probably in the last 30 or 40 years. I mean, we have a huge amount of successes, started with polio vaccine more than 60 years ago, and now hepatitis vaccines, pneumonia vaccines, influenza vaccines. You know, that's the whole idea, is to really kind of give your body a chance to have that immune reaction with something that's more benign, as opposed to actually getting infected. That's really the idea. And all of these, as you're going to show us, I think in a minute, Pat, all of these vaccines work a little bit differently. They're made a slightly different way to stimulate the immune system in a slightly different way. And that's kind of the beauty of this effort that we've done through Operation Warp Speed, is to really try all of these different approaches at the same time. So if one of them may not work as well as we want, we have another one that's right there. So you don't have to wait another couple of months or years to develop it again. Usually when you do vaccines, you try one method first, then you go to another one and another one. This way you're doing it all in parallel, which I think was a great idea.
So let's get into that, because I think one of the questions, one of the concerns of confusion, probably to the lay public, is how do they work? And you know, we've talked about the why. Let me go a little bit into the how. And we won't go too deep into the science, but it's important for the audience to understand the differences between these vaccines. On the one hand, the way the vaccine works, as as you described, we've now modernized because of the whole world of genomics and sequencing, as opposed to just taking the live or attenuated virus itself and putting it into you to see if that could create immunity. We have now the tools of genomics. And genomics says there's a thing called DNA, which is the gene. Then the next thing called RNA, which is going downstream of the gene that talks to that gene and makes ultimately the protein. So if you look at this, that's the cargo. That's the cargo of the COVID cargo. So the virus itself, if one wants to take the cargo, we could actually take this cargo from COVID, and you're either going to take the DNA from COVID, or you're going to take what's downstream of that from COVID, called the RNA, or you're going to take the protein. And these are the different approaches that these companies have taken. AstraZeneca and Johnson & Johnson has used the DNA sequence from the COVID. Moderna and Pfizer have used the RNA from COVID, and Novavax is using what we call a protein. At the end of the day, we need to figure out how to get that cargo into your body. And the two companies, AstraZeneca or Oxford, has used this common virus that you and I have, called the adenovirus. And Moderna, on the other hand, that takes the RNA, have used a little fatty globule called a liposome, and this liposome delivers it. And Novavax has used a gooey sort of material that acts as an immunogenic material. At the end of the day, once we've transported this cargo, what we really want is this protein in your body. And what does these proteins produce? And each one of them have taken the strategy of looking on the outside of the virus, on the surface of the virus, because this thing called spike. So I think that is the strategy of the first wave. And it's not an unreasonable strategy, because the usual way of vaccinating is to try and find an antibody to block the entry of this virus into your body. And that is the mechanism, one of the mechanisms of immunity. But let's dive a little bit deeper into this strategy of spike and really ask Adam what she's thinking about how this vaccine works. Because on the one hand, there's spike, on the other hand, there's an inner protein called nucleic capsid. And at the end of the day, they are basically two potent mechanisms to protect your body. One is the antibodies to prevent the virus from entering into the cell, and the other one is T cells to actually clear the virus by killing the cell itself. So Adam, why don't you comment on your thoughts on this particular strategy and how you think this works?
So let's step back just a little bit and it's kind of really sophisticated immunology, and we're not going to get too deep into it. I mean, it's really fascinating stuff, but there's a master cell that controls your response to anything that's induced into your body and determines the immune response to it. It's called a dendritic cell. And it really, in a way, is kind of the brain of your immune system. And what we're doing with all of these vaccines, whether it's DNA, RNA, or protein, is that we're somehow getting that particle of DNA, of RNA, of protein into that dendritic cell. And depending on kind of what that composition of that thing is, whether it's RNA, DNA, protein, will depend on kind of what immune response you get. And in some cases, you have to add this extra thing called an adjuvant, and that's either some sort of chemical molecule or some other kind of protein to kind of help those dendritic cells get stimulated. Because what you're trying to do is that dendritic cell, depending on what we give to it, depending on what we feed it, will give you a very specific and a very kind of a very specific type of immune response. And I think, what you want, as Pat said, is you want these antibodies, what are called neutralizing antibodies, that block the binding of the virus to cells in your body, whether they be in your nose, your lung, wherever they bind. We now know that the virus starts up in your nose and your upper airways. It eventually is aspirated if it lasts long enough down into your lower lungs. And so, what you want is you want to develop antibodies to try to block that from happening. Those are called neutralizing antibodies. But on the other hand, I think what we've learned and what we're learning, again, we learn every single day there's a new paper, a fabulous paper in some of our major journals that guys like Pat and I talk about when they come out, and all scientists really, and all doctors talk about this, where, we're learning that there are very specific types of immune responses that you're going to get from these vaccines that probably are going to be more long lasting. For example, we know that the antibody response, is neutralizing antibody response, is what seems to be important for the first couple months. But on the other hand, there are T cell responses that may confer even longer lasting immunity. We don't know for sure because it's all so new. It's only been around for 8 months. But on the other hand, if you analogize to other diseases like SARS, for example, which is kind of like SARS-CoV-2, like COVID-19, that if you have some certain T cell responses, they can last up to 17 years, and so the issue is that when we're doing, these experiments with vaccines, when we're testing them out, obviously the proof is in the pudding. It's preventing infection in people. That's what these first kind of, when we first start seeing the results, hopefully in the next few weeks of these initial trials, that's the thing everybody's going to be looking at. How many infections were prevented. But beyond that, what we're really looking at also is what is the type of immune response that's preventing that infection? Is it just antibodies? Or is it antibodies and T cells? And there's various flavors of T cells. There's a cell called a CD4, there's a cell called a CD8. And I think that this is all really important for when people like me and other physicians and scientists look at the results of these studies. What we're trying to do is see what the shape of that immune response is to kind of help us figure out how long lasting that immunity that you get from the vaccine may be. So that's kind of, I guess, answering your question, I think.
Yeah, it does. And I think if we go to the next slide, it really leads us to how long do these antibodies last following an infection? And we talked about if it's antibodies, if you get a natural infection, how long they last, and if you give a vaccine that actually stimulates just antibodies, what is your prediction or thought? And obviously, as you said, we don't know.
We don't know because it's so new, and we can look back at. The only way we can do it, and what a lot of us have done, is you've said, okay, we can't do this with SARS-CoV-2, so we have to look at SARS. But SARS-CoV-2 and SARS are different. They really are going to be in some ways quite a little bit different. I think that maybe not a lot different, but different enough right now that we're not quite sure that we can analogize completely from one to the other. But we know that in SARS, that the antibody response, depending on kind of who you talk to and what experiments and what clinical studies you look at, can be anywhere from a couple months to, in some cases, a year or two. And I think that we're trying to see the same thing here. There are antibody responses. It appears, at least initially, we thought they were going to last a long time. Now there are more recent studies that suggest the antibody response lasts maybe 3 to 6 months. But again, we don't know. We just don't know yet because we just haven't studied the disease long enough. That's part of the issue here. But I think a lot of people are converging on the idea, at least initially, with the idea that this can all change. That we're talking probably, on the order of, 4 months, 5 months, 6 months. I think that's the number. I don't know what you think about this now, Pat.
Well, the way I look at it, if you look at this next slide, if I may, this is what is of concern. You talk about SARS-CoV, the first one in 2003, and now SARS-CoV-2. What's happened in the 70 years change is this mutation. The spike has actually mutated. And sadly, it's mutated to the point that it's 20 times more infective than SARS-CoV-1. So you have this combination of concerns of having an antibody, we're not sure how long it lasts, and if it is an antibody in the mutation environment of a SARS-CoV, even 2, will those antibodies actually be even neutralizing? So, which then really takes us to where you started this whole conversation. As a cancer doctor, and that's the perspective which I took it, when you ask what's my perspective, I look upon this as how we would treat cancer. You and I have looked at trying to develop cancer vaccines, and I believe that you need the combination of both antibodies and T cells. And that is really where I think is probably the best bang for your buck. Because we do know that you do have memory T cells. talk a little bit about those memory T cells, because there's not only memory T cells now that we found in multiple papers, 17 years. There's also this concept of epitopes that we had on our show, Dr. Sethi and Dr. Crody would talk about T cell epitopes. And now there's just a paper, just even as recently as yesterday, about in 73 patients with SARS, in which they isolated and tried to understand what was the basis of the immunity. So maybe if you could just fill us in a little bit more on that, Adam.
Yeah, I mean, I think it's really interesting. So an epitope is just an area of the protein that either the T cell or the antibody recognizes. That's kind of the most important part of it. You know, proteins are just a sequence of these things called amino acids, or just, you can look at them as letters, you know, and there are 20 of them. Actually, there are more, but just for the sake of argument, let's say 20. And it's that sequence that is unique. That's what makes a protein unique, that unique amino acid sequence. And the immune system, either B cells or T cells, recognize specific epitopes. And one of the issues here that we've tried to figure out over the last several months or so, as we've learned more about this disease, is which epitopes are exactly those that get the best immune response. And initially, we had all focused on the spike protein, and naturally, because that's what we thought it was. But I think what's interesting, and this is all very, very, very recent data, literally papers that were published in the last week or two, as you just said, it may be that some of these epitopes are not just in the spike, that they're in the nucleocapsid protein, they're in something called the ORF1ab protein complex, which is basically a huge protein that is cleaved into probably 5 or 6 or 7 other proteins. You know, there's that. There's something called ORF3a, which is another protein of the virus. So I think that it's a little bit more complicated. But what's interesting is that it appears that there are commonalities, that they're what are called invariant sequences. That is, you know, you had talked before about the virus mutating, but apparently, despite the fact that the virus is mutating, there appear to be sequences that are constant. And those seem to be the ones where most of these epitopes seem to reside. This is literally brand new data that literally has come out in the last week or two. And this is why this is changing so much. And I think, you know, this is going to help us, because it's going to help us in vaccine design going forward. It'll help us, I think, even more in trying to figure out who is really immune to this. You know, because as we all know, a lot of people, the vast majority of people who get this are asymptomatic. And they get it, they're minimally symptomatic. Maybe they'll have sniffles or something, or a cold, and they'll get over it. And we don't know whether they've been exposed to the virus or not. We'd like to know that. And I think we're going to know that by using some of these epitopes to try to figure out what T cells are actually we can detect in your body. That's the beauty of some of this newer data that's coming out. It's going to give us a roadmap to try to figure that out.
So let me reduce that to a little bit more. I think you and I understand that, but with regard to the English,
right? I know it's kind of, sometimes we do that. We get a little bit out of control here.
So this is the spike that is one of the proteins that has been used. In fact, as I said, the 5 phase 3 trials are all again going after this particular protein. And it looks like that the predominant way of actually creating this vaccine is to create an antibody to this protein. But as you said, what's coming out now and very, very recent is that in order to stimulate T cells, while spike does stimulate T cells, what seems to be predominant is inside this virus, inside the body of the virus. And that's called the nucleocapsid protein or the ORF protein. So there's proteins inside there that are actually responsible for the virus to replicate and structurally responsible. And they really are very powerful stimulants for T cells. So the whole concept then is that if you had proteins that are different variants of these proteins, and you try to train your body against both of them, that gives us hope.
Yeah, that's exactly right. And I think that, you know, the more protection you have, the more ways of protection, the better. And it turns out the T cell response takes a little bit longer to happen than the antibody response. And I think that, but I think on the counter to that, the longer the T cell response appears to be longer lasting. So even though, you know, you get kind of this short burst of antibody response, you get this gradual kind of T cell response that may last for a lot longer time.
And that's really been the concern, right? How long do these antibodies last, even from a natural infection? And as you could see, they wane.
Correct.
And then what would happen? How long would they last from a injection or a vaccine? And how long do these
Correct.
T cells last? And the history we have, as you said now, memory T cells that go for years, maybe. So
Yeah.
I think the key to a vaccine is not just it's safe, clearly, first, safe. Secondly, that it gives you some level of protection, and antibodies do. And but mostly, thirdly, it gives you a long duration of protection. So you don't need to have a shot every year, and you at least don't accommodate if this thing mutates. So taking that to the next level, if I may have the next slide then, and I think this is why this is so important, because it is really important for the public to have trust in these vaccines. Really, really, really important. And the one question that is of great concern to the public health community is when the vaccine arrives, how many people will take it? And if I can have the next slide, is why is there this distrust of vaccines? Can you maybe speak to that a little bit, and how do we lay the fears of our readers not to have distrust of vaccines?
Yeah, I mean, I think that, there have been issues with vaccines in the past. I mean, I think the dengue virus vaccine is a perfect example in the Philippines from a few years ago. And I think these are events that can happen. But on the other hand, there's two ways of getting immunity to a vaccine. One is being vaccinated, and one's getting it. And, that's the big mystery that physicians and all of us who have spent a lot of time talking and thinking about this are really struggling with. That we're always with 80,000 infections a day that we saw right now, a lot of people are getting it and are getting immune. But how many of those people are really getting sick? And we can talk about that a little bit later. But, instead of all those people getting really sick, maybe if you give them a vaccine, we could get through this and get everybody immune without getting a lot of people sick. And I think that's the real mystery that physicians are having right now. And I'll tell you, I think that, I want to be, I'll do it. I mean, a lot of us will do it. Physicians are going to stand up and we're going to say, let us be the guinea pigs. Okay. Let us be, if we're not around, if something happens to us, you don't have us, I'm sorry. But on the other hand, I'm willing to be the guinea pig. I'm willing to be the first one doing this. I don't know, there may be side effects to it. We're seeing that because whenever you induce an immune response in somebody, you always have the possibility, albeit extraordinarily rare, of having an adverse immune response to something. And that's always been the fear. And that's why, in general, we tend to do vaccine trials that last a long time. But on the other hand, we're in a kind of a bind here. We've shut our country down. There's a lot of uncertainty about what's going to happen next. And I think that we really have to balance the equities here. And I think that's really the dilemma we as a society have.
My view is that people are worried about this idea of warp speed, or speed of clinical trials, or the adverse events. And I want to show, maybe from my perspective, what I'm watching, the science is really at least being deeply considered by the FDA. I think I have communications directly in the leadership of the FDA, both in the vaccine division and the commissioner, are scientists, deep scientists and public servants. So I want to show at least our audience that that's the case. The other issue about these adverse events you brought up, these happen. It's actually the fact that you have adverse events that now you've seen in some of these should not be concerning, because it's actually a sign of actually safety, a responsibility that's happening. But this then brings us, if I may, to the next slide.
Yeah, well, you're talking, I want to re-emphasize that point, Pat. I cannot emphasize more how deeply people are thinking about this and how seriously they're taking it. They understand that we're trying to develop this faster than usual, and they're taking extra care to be sure that anything we give to the public really is as tested and as considered as possibly we can, because we know we're doing this faster than normal. But on the other hand, it doesn't mean it's not safer than normal. If anything, it's safer than we normally do because we're taking extra steps. And I think that's something really, I'm glad you brought that up, because it really needs to be emphasized to people that again, That's why I'm saying I'll be the first one. I mean, I don't mind. I mean, I'm not in the first 30 or 40,000 people who got it. But on the other hand, I cannot emphasize that enough. I agree with you. I think the people in the FDA, in our government, the people that are working incredibly hard on this to try to make sure this works, really are doing everything they possibly can to be ensure that whatever we give people is as safe as it can possibly be. But there are going to be adverse events. There are adverse events with anything.
And you have to balance that against what we're seeing here on this map now. And you heard the talk about herd immunity. And I think that's not only a ludicrous idea, but almost unethical, because now you will actually truly face millions of deaths, independent of the vaccine, if you hope that self-infection. Now, people agree to disagree, and maybe we can talk about that, because you may want to talk about what is the current death rate. Is it it's reducing now? It's going down now, or not?
Yeah, I mean, I think it's a fascinating question, and it's a tough one because no one wants people to die from this. No one wants people to suffer. No one. But we're trying to figure out what's going on. When someone says herd immunity, I don't think they're saying let's get everyone infected. I don't think. I think it's been mischaracterized a little bit. I think the real question is, let's find out how many people really have immunity, long-lasting immunity to the virus. Does long-lasting immunity exist? I mean, that's a question no one can answer right now. We're having this question right now about vaccines, which is the same question with natural infection. Do we really have long-lasting T cells that have been made? If so, how many people in this population of the United States or the world really have them? And that's really the question. It's not letting people get infected. It's more estimating, getting that point estimate of how many people we really have to vaccinate at the end of the day. They're not mutually exclusive. They're all part and parcel of the same issue, which is if we already know, for example, that at least 10% of the US population, I mean, there were some very nice antibody studies that were done out of dialysate. They went all around the country and they looked at renal dialysis centers and looked at the level of antibodies to SARS-CoV-2 in the dialysis. You get dialyzed, there's all this fluid, and they can do antibody testing on it. And that was about 10, it was like 9.2%, and that was in July. So you can imagine it's a little bit higher. But we don't know the things we don't know. We don't know how long that lasts. We don't know, is there T cell immunity associated with it too, just like we expect to be with a vaccine? These are unanswered questions. And I agree, letting it run rampant throughout the population and herd immunity, that's no one wants that to happen. And I think that I agree with you 100%. It's not the way to do it. But on the other hand, what I would want to know is how many people are truly immune right now at any time. And I wish we could know that, because we're all flying blind, because no one knows that number. I mean, what do you think, Pat? I mean, if we just look at the PCR part of it, it's what, 3%, 5%, something like that. And then when we look at the antibody testing, at least as of July, it was 10%.
I don't want to put fear again into the audience, but not only don't we know, we don't even have standardized tests to know.
Correct. Absolutely. I agree 100%. These are all the questions we have to answer. I agree, but I think that what at least I want to emphasize is that people are actively trying to figure this out. And the debates people are having back and forth as docs, like we're doing right now, are a natural part of the scientific process. We want the answer now, but that's not the way science works. It's that we all have these disagreements and discussions about things, and they're all professional. And we try to figure out, based on the data as it comes in, where the hypothesis is going, where the reality of the situation is going. And that's really the issue.
You need to know who's immune. Now you need to go from a different question real soon, over the next 6 months, I believe, is do you have immunity from the infection? And do you have immunity that's long-lasting from the vaccination? And then what tests are you going to be doing? Is it an antibody test, a T-cell test? Do you have a T-cell test? So people get very confused. We've been in the show trying to compare and explain a PCR test, a rapid test, an antigen test, what that means. In my mind, you take those tests just to make sure you're not infective, to protect yourselves from others, so we don't have this ongoing pandemic. But this is going to be a different question next, and very soon. And what kind of tests do we need to actually prove that you have immunity? I think we have some answers. I was just on the phone this very morning with somebody who was a former head of NIH animal testing facilities, and they're trying to create a T-cell test. Now you heard about antibody test, but a T-cell test is something that needs to be. But let's talk about this. You're saying death rates are going down according to a recent study. What's your opinion about that?
I think it's a great question. I think that we don't know why, but we do know, looking at other pandemics that we've had throughout history, from the influenza pandemic of 1918, there were clearly, depending on the wave of the pandemic, there were different death rates. I mean, influenza was really interesting. There was an early phase in the spring of 1918 that didn't seem to be severe. Then in the winter of 1918, it was severe. Then it got less severe again. There's actually data from Connecticut that the 1918 pandemic started in New London, which is the eastern part of the state, and over a period of 4 weeks, as it went to the western part of the state, kind of toward Westport and Bridgeport and Fairfield, Connecticut, that apparently the death rate of the virus got less. And these are really important questions. We don't know why that's happening. I mean, and again, there are a lot of theories, there are a lot of hypotheses. Some people don't even believe it. First, you have to even believe that that's even happening. But I think we're clearly getting data, both from at least the first 2 big studies that were at least in preprint form, and I think one's been published. One was from NYU, where they looked at their death rate over a period of like 4 or 5 months last spring. And they found that the death rate across all age groups, one of the questions was, well, it's only younger people getting it now, so that there are not as many deaths. But they found in over all age groups, all morbidity classifications, which means how sick the people were when they came in, across all age groups, people actually had less death toward the end of it per case. So what we call the infection fatality rate, or the case fatality rate, was less. They found the same thing in a very large study in the United Kingdom. And so we're trying to figure out why that is. It's very interesting when you look at that paper. You look at the paper that was done at NYU, you find that the viral load of the patients appeared to be less as you went further in the pandemic. And so why is that? Is that because the virus has a mutation in it? Is it because we have better immunity? Is it because more people are less susceptible to it, so there's less viral load when they get it? We just don't know. And I think these things have to be sorted out. First of all, we have to believe it. I mean, before you even go that far, you have to believe that first. And, I think that the point here, I think I'm trying to stress, and again, we're oncologists, Pat, you and I, we like to be optimistic. We're optimistic people. We have to be. And, is that I just want to stress the docs are on this. I mean, it looks like we're flailing around and we're arguing with each other in the press and this and that. Docs do this all the time. This is what we do. It's just we usually do it in private and you guys don't look at us. We're usually just kind of arguing at meetings or in conferences and things like that, and no one cares about what we say. But the problem is that because this affects absolutely every person in the world, people are hanging on our every sentence. And I think that just people need to understand that we're doing this, and it's going to happen. We're going to figure this out. It looks terrible now with 80,000 infections. I know, but I think that there are some lights at the end of the tunnel here.
So let me give you my theory. Virus is like cancer, as you and I know, adapts. I think this virus, like every other virus, and is truly this intelligent machine. It does not want to kill the host, because the host, meaning you and I, when it infects, is its only means of actually growing. It has no other mechanism to grow other than using you and I. So I believe it's attenuating. It does attenuate to, one, increase infectivity, but maybe reduce the death rate. However, I'm really concerned, and if I go to the next slide, and I'm concerned about this. This idea of this long haulers, this virus, in my mind, behaves very much like a cancer cell, a leukemia, because it penetrates, pops through the blood, into the blood vessels, and it creates a vasculitis across all organs. So we just had a show just a couple of months ago with Dr. Carlos Codon. We did 107 autopsies and found in the heart, in the brain, microthrombi, if I have the next slide. Every organ that you can think of, this virus hits. So my fear about, even while the death rate is down, if it is, we cannot assume that that's a good thing because of these issues of unknown chronic long-term disease. And to me, that actually speaks even more so of how and why a vaccine should be out there. I think we've also learned a lot in this acute phase when the patients go into the ICU, when they were giving PEEP, and in fact, that could have been hurting the lungs. We've learned now with monoclonal antibodies, at least, it can block and mitigate some of the viral loads, etc. So I think the medical community has learned very fast how to deal with these acute onsets. But I do believe that we have to address this thing for the long haul by finding the vaccine to prevent these long haulers.
This is clearly something that is an immune reaction to the virus. We have no idea what the consequences of that long-term immune reaction are going to be in a percentage of people. No doubt about it. But I think one thing that we haven't done enough of in this disease is really study the asymptomatic people. We've really looked very carefully at the people in the ICU, those that are hospitalized, but our focus has been on that. But in reality, the vast majority of infections are asymptomatic or minimally symptomatic. They're detected. Someone stays at home for a few days. They're 10 days. They have to stay home because of quarantine. And then they're okay. Clearly, the people who are hospitalized, infected, get to the point where they're on oxygen in a hospital. There definitely is a long COVID syndrome in a lot of those people. I agree with you.
Do you believe these asymptomatic people have less opportunity to have immunity, generate less immunity?
I think it's the opposite. I think they probably already have enough of what we call the innate immune system as opposed to the adaptive immune system. In other words, they probably have a very strong ability, a non-specific ability to get rid of the virus, as opposed to actually mounting a true immune response with antibodies and T cells. And what that means, ultimately, I don't know. I think, again, this is all unknown right now. But clearly, a lot of the literature that's starting to develop around this suggests there are going to be people, and we don't know how many, who have a very strong immune system, who probably children is a perfect example. Children have a very strong, what we call innate immune system. So the vast majority of kids are able to kind of really, deal with this very quickly. Not everybody, and, we don't know who. But on the other hand, I think that, if you have a very strong, what we call innate immune response, a non-specific immune response, does that mean you don't get long-lasting immunity? These are questions we don't know. And I think these are the sort of things that hopefully over the next month to year, months, hopefully, as opposed to years, but you never know, we're going to kind of answer as time goes on.
So let's get back to basics now. Now I think we've turned our attention from at least the vaccine, the hopes of the vaccine, how it works, why you should trust it. We're still not sure about how long it would work. But at least we need to do something to say we are in where we are right now, and the basics of prevention still to this day apply. Hand washing, social distancing, no large gathering, and most importantly, masks. And I cannot emphasize more how important that is, and maybe you'd like to speak to that, Adam, because I think we need our audience to understand these basics.
I agree. These are very, very important things. The real thing about masks and social distancing, for example, that isn't really kind of emphasized is that a mask is important when you can't socially distance, okay? And so if you're 6 feet apart from somebody, you can wear a mask if you want, but on the other hand, that's an important thing that the CDC has emphasized to everybody. It kind of gets lost in transmission, is that masks, and most people can't socially distance. That's the point. You start you go to a party with somebody, you start 6 feet apart. There's no way you're going to be, by the end of the party, there's no way you're not going to be less than 6 feet apart from somebody. So, the issue is that, therefore, that's why a mask is important. And I think the mask isn't important for everybody. It's not important for you. That's really important too. It's like, everybody says it's not you, it's me, or it's not me, it's you. A mask is not about me. A mask is about me protecting you. And I think it's for that person. Not everybody can spread this virus when they're infected, which we have this thing called the concept. I'm sure you've talked about it in other shows about the super spreader. It's that person who's very infectious to everybody, doesn't know it, and is wearing a mask. Now, it's not going to be perfect because masks are not perfect, as we're going to find out. I think, and there's some studies coming out, the whole mask business has always been controversial, but I think that it's not a hard thing to do.
It truly is not a hard thing to do, and I'm now seeing studies where there are some of the filters and the testing, and the viral load is significant. I mean, the drop in viral load is significant. Yeah. Let's turn to the next subject here. And what I want to do now, Adam, is turn to some viewers' questions. And this question from Teresa is risk from exposure cumulative? In other words, if I'm exposed to a small amount of virus, are the odds good that my body will shake it off? But if I'm exposed to a lot of virus, like a healthcare worker, can the virus overwhelm my system? How would you respond?
These are great questions. They're great questions. I think that, no one knows the answer to it. And I'll just give you at least one thought. I mean, there's other thoughts too, that a little bit of virus may be okay to inoculate you enough to develop an immune response, a long-lasting immune response. Some people feel that's the whole point. Someone has gone around recently, a group from the University of San Francisco, that said, and again, this is very controversial because literally they published it 1 week in the New England Journal. There's now a rebuttal 2 weeks later. This is how controversial some of these things are. But some people feel that wearing a mask gives you a smaller inoculum of virus. And so if in other words, you contact somebody who was wearing a mask and they happen to transmit it to you, you get a smaller amount. So therefore, you may be able to get immunized to it. That's one option. So I don't know the answer. I think personally, I'm curious to hear your view on this, Pat. My own view is I don't think it's cumulative. I think that, I think that it's the degree. How can I put it this way? The people that seem to get exposed the worst, when this first started and we started looking back at all this, it was being crowded together in an area of poor ventilation for more than like 20 minutes to half an hour. I mean, that seemed to be like sitting at a table or sitting in an airplane is the perfect example. You're sitting next to somebody, either asymptomatic or they're sniffly, they don't really know what's going on, and you're right next to them and for a long time. That seems to me to be the answer. Now, the CDC is kind of changing their guidelines in this. They just did recently to like where it's not now an exposure for 20 minutes, but rather a cumulative exposure over a day that equals 20 minutes to half an hour. And again, this just reflects the kind of uncertainty right now about what's going on. So my own view is that it could be cumulative, but if I had to guess right now, I would say no, but I could be wrong. I don't know what you think about that.
Well, I think it depends on your immune system. I think if you have a good immune system, and as you said, both innate and T cells, you clear it. And you may not be symptomatic and clear it. Let's go to the next question. So the next question is from Suresh, who said, I had a kidney transplant a couple of years ago. What's the impact of potential vaccines on patients like me who take immunosuppressants?
I don't know if maybe Pat, you know better than me. I don't know whether they allowed people who were immunosuppressed, like people who are post-kidney transplant on these vaccine trials. I do not think they did. I think it's probably something that we're going to have to explore, assuming the vaccines work on the healthier, non-immunosuppressed people. I think this is an area of clinical trials that are going to have to be done. I don't know what your thoughts on that. It's a good question.
In our immunosuppressed cancer patients, the good news is when we're given our adenovirus, we're able to actually convert their bodies to generate CD4 and CD8 T cells to the sequence of the cancer sequence, like carcinoma embryonic angioma, or CEA, which is part of the cancer, even though they're immunosuppressed from the immunotherapy, from the chemotherapy, etc. So the difference, however, we had to give these vaccines repeatedly, and so that's another challenge. Can you have a delivery system that can be given repeatedly, and your body itself doesn't create an antibody to the delivery system? But I think the answer still has to be figured out in this area of COVID. COVID is a scary virus. its own self, not the vaccine, but the virus itself, has a way of immunosuppressing your T cells. And you've talked about this yourself, you've written about it in papers, how it has, the virus itself as a natural infection, has a way of actually putting your T cells and dendritic cells to sleep, so to speak.
Yeah, it does. And I think that's kind of, that's really, and how it does that molecularly is kind of, I think people are just starting to kind of understand this. And it may actually have something to do at the end of the day. If the virus really is attenuating, it may be through kind of this mechanism. And then there are receptors other than ACE2 that we're learning that the virus uses. And some of these receptors are on various immune cells. And I think that what tends to happen in early infection is that the virus, in a way of kind of trying to trick the immune system and hide from the immune system, it kind of infects these various immune cells with these other receptors that are not ACE2. And kind of then it's almost like a Trojan horse. The immune cells kind of go throughout your body and then suddenly find the ACE2 cell, the ACE2 expressing cells, like in your lung, for example, the pneumocytes and the endothelial cells. And then kind of in like a Trojan horse fashion, they kind of sneak up to it and then spit the virus out onto those cells. And a lot of viruses tend to do that. And, it's called transinfection is what people are calling it. It's very common in other viruses. So the issue is that this may be part of the whole pathogenesis of the virus that, again, we're learning as we go here. This is a theory. It may be wrong. It may be right. But I think that some of the data that's now coming out suggests that infection of these kind of immune cells, the T cells, the dendritic cells, to kind of trick the immune system for the first couple of days may be an important part of SARS-CoV-2 infections.
I have a theory, maybe I'll share with you, and we'll do that offline, but maybe I'll do it online. And I think it's part of the trick of this virus, actually. There's a thing called type 1 interferon, as you know, that if you and I were to get sick with an infection, your immune cell system throws out a signal and says, hey, I'm sick. And you get sick, and you get a temperature, you get a fever. So why do you have this asymptomatic state of this, as you said? And I think this virus, and I think especially the protein N, has a way of actually going in and turning off that type 1 interferon and actually hiding from the T cells. And in so doing, as it hides, it actually causes the T cells themselves to die. But anyway, it's a theory. I hope that over time we will be able to look at that, and it's another way of what we call immune evasion. That's why I believe this virus behaves very much like a cancer. Cancer does that. It causes this immune evasion.
One thing that people have just found is that there's a very specialized cell of the body called the plasmacytoid dendritic cell. It's a mouthful, but that's a cell that makes type 1 interferon. And it turns out that the ratio, those type 1, these plasmacytoid dendritic cells in acute infection are reduced dramatically. In fact, to the point where they're thinking of using that as a marker of disease severity. And so, you're right up there, Pat. I think you're right that if somehow you're affecting like these cells that make type 1 interferon, then it's likely that you won't get any symptoms because you're not making type 1 interferon. It fits with a lot of data that's kind of starting to be developed.
And that's the beauty of science, right? As you sort of understand the molecular mechanism deep down, you then can figure out a vaccine to outsmart that. So I think by understanding the science, and that's why I hope our viewers understand that there are so many dedicated scientists across the world spending literally every day on this pandemic of our lifetime to try and address this. So let me, before we close, to go to the last question, if there is, and this is an interesting question. How safe is swimming? Does the chlorine in the water offer protection from the coronavirus, and would you go surfing?
I think that chlorine probably does protect people. I think that, I think the other thing that protects people that we're finding is vitamin D. I think that people are learning, and again, we're debating the quality of the data right now about how good these data really are. But people have found that if you have normal levels of vitamin D, you tend to do better. You don't get as infected as much, and if you do get infected, it's not as severe. It could account. Some people believe there's seasonality to the viruses, although we're not quite. Although it's hard to know with what we just saw. Was it seasonal or not? Now they're spiking again. Is it because there's less UV light out, so people have less vitamin D? I don't think anybody knows. But I think being out surfing, you're getting a lot of vitamin D. I mean, yeah, if you're wearing a whole surf suit, your whole wetsuit, you may not be getting as much vitamin D as you want. But on the other hand, I think that salt water has always been good. I think that there's this whole thing that saline flushes of your nose actually help the virus. So I think salt water is not a bad idea. I mean, these are simple things. Again, are they right? Are they wrong? I think things like making sure your vitamin D level is within normal range over 30. I think making sure you don't have, because we know that hyperglycemia, that is diabetes, makes this disease worse. Making sure that you check if you're old enough that your hemoglobin A1C, which is a marker of diabetes, is low, is below 5.4%. You make sure your cholesterol is under control, because some people think high cholesterol can make this worse. I mean, these are normal, and these are not like there are papers on all this. This is not like we're just talking about it. These are healthy things that people can do I mean, it's the same thing with cancer. People come to me, and they probably come to you, Pat, all the time, and they say, what can I do personally to help me fight cancer? And it's the normal healthy things we always tell people. And I think that a lot of that probably applies to this disease as well. Is it a cure-all? Of course not. But on the other hand, if you want to feel like you want to take a little bit of control of what's going on, just making sure your cholesterol's under control, your sugar's under control, your weight's under control, get out, get sunlight, make sure your vitamin D is normal. These are simple things that we can do that may help. I don't think any of them are going to hurt, and they're all good medicine.
Now that you bring up vitamin D, and I said to myself, is this just an old wives' tale, or is this real? And fascinatingly, as I was going down the theory of why is this virus so silent in your body and how does it suppress the immune system? And there was one not relatively obscure paper that shows that vitamin D increases a thing called autophagosomes. Now, autophagosomes is a thing in your dendritic cells that actually has ties to a thing called lysosomes, which is acid. So this N protein, if it goes into autophagosomes, and vitamin D augments autophagosomes, it'll break it up and therefore expose your immune system to N. So you think these are old wives' tale, and there's some very fundamental scientific reasons for all of these things. I worry, however, also about the water, because we do know that ACE receptors are in our gut, and therefore, contaminants, stool, etc., gets in, and these viruses could still survive. But this is an important question, an interesting question. It also exposes what we don't know. But I think you're right. Sun is good. Vitamin D is good. And
right.
Chlorine is
These are all healthy things to do. I mean, these are all very, very healthy things we can do. And I think that, they're not going to hurt you. And in fact, if they don't help you against, SARS-CoV-2, they're definitely going to help your overall health. I mean, maintaining, these are things docs have been trying to tell people for years. Keep your cholesterol down, make sure you get enough vitamin D, keep your weight down. These are be sure don't make sure if you have try to control if you have diabetes, try to control it. These are not way out there things. These are things that are going to help your overall health regardless, and in fact may help against the virus. We just don't know.
So in essence, keep healthy, have less stress. So Adam, we always close the show with give our viewers a glimmer of hope. What would you see as a sign of where we think we're going?
My own personal opinion, and again, being optimist, and we just don't know the timing of this, is that I really think that the virus is likely attenuating to some degree. I think we just don't know how fast it's going to be. We don't know the clinical consequences of that, so that's hopeful. I personally think that the vaccines will give us some sort of broad immunity. How long that lasts, we don't know, but the hope is that enough of us get the vaccine at the right time that we at least get enough to break the cycle, break the transmission cycle. And I think that, at least to some degree, and I think that's where the hope is going to be. I think, it looks terrible now. We've got all these infections, and we're kind of uncertain about the death rate a little bit, as we've been talking about. But pandemics have to end. They always do. This is what I'm telling people now. They always do. And they will end. And our goal here is to have this end with as little death and disability as we can. There's going to be death and disability, unfortunately, no matter what we do. But our goal of everybody who's doing this, and there's an enormous amount of very serious people, a lot of people you don't see on the news, every night, being some talking head, there's a lot of people out there that are really a guy like me, who I'm a cancer guy. I deal with cancer. I've decided to try to work on this for a while, to try to provide whatever input I can. And there's a lot of people who are trying to do this. And I just want to give people hope that there's a lot of people out there that you don't see that are working really, really hard. And I think that to come up with things that are going to beat this. It looks bad right now with all these infections, but there really is hope that this is going to end. Just a question of when.
Well, my light of hope is people like yourselves, i.e. the collaboration, the scientific insights, the amazing amount of work that people are doing as we begin to understand literally day by day how this virus works, what it's doing, how to outsmart it. With all disclosure, I did not feel appropriate for me to talk about our own work in this.
Which is great, by the way. But I didn't do it in the interest of like full disclosure. I would have loved to talk about your stuff, but I didn't.
No. I think it was important for us for me to look. I think my hope, my internal hope, is that at least I'm so proud of our scientists, literally working 24/7. And the fact that we are now in phase 1 clinical trials, we've taken a very different approach. We've taken an approach that, based on all our work on cancer, that we want to drive T cells. But that's not for this episode. However, I'm internally hopeful. And like you, as you said, would you take a vaccine based on the science of what we're all doing? The answer to me is yes. So with that, Adam, I want to thank you for joining us, and hope we can do this again. I'm sure we'll be able to do this again, and look forward to another talk. And thank you for joining us on Second Opinion.
Thank you very much for having me, Pat. Thank you very much. It's been fun.
Stay safe.
Thank you. You too. Take care.
Okay. Bye-bye.